if we take a slab of tissue and we think about whether this is skin or some membranes in your body or a lining to an organ, it's going to contain various things, and some of those are going to scatter light that might shine through. Other constituents will absorb light, and if we act on the surface of this tissue with a laser, like we do in the lab, some of it's going to be just reflected off the surface, like off of the top of that oil film. Some of it will interact with those scattering parts and be re-emitted. Some is going to find its way through and be transmitted. And we all know that, see, I have a laser pointer here. If I put it by my, oh, the room's not dark enough. Anyway, if the room were dark, you'd see I could shine the red light right through my finger, and a lot of light does get transmitted through. But the part that is of interest to us is the part that goes into the tissue and gets absorbed by certain structures. And whether or not it gets absorbed or passes through is wavelength dependent, just like my plexiglass is opaque to infrared, but it's clear to visible light. Likewise, the things in tissue, some wavelengths are going to be absorbed and it'll be opaque, whereas others will send it through. So one nice thing about lasers in interacting with tissue is by choosing the right wavelength, we can choose which constituents we're going to act on in the tissue. For us, you'll see that we are acting primarily on connective tissue and collagen to do what we want to do. So each one of those acts as a little heat source because it's absorbing. And here's just an example of, on this axis, it's a relative measure of how much energy or photons are being absorbed by the dark line is haemoglobin, and the dashed line is just water. And from here on out, they're very similar. But at lower wavelengths, you can see that the hemoglobin will be very absorptive and the water is clear, which is why we know water for the visible spectrum from here down is clear. So it's not absorbing, it's passing it through. So by choosing a wavelength, we can selectively act on different components. And absorption is just the conversion of that radiant energy, the light energy, and the photons into heat. And water mainly absorbs in that infrared range, proteins absorb in the visible range, chromophores in the ultraviolet range, and we can characterize this by a coefficient where we can add up all the different contributions of what's absorbing in our tissue to know how much is being absorbed. Another important characteristic is, when I mentioned the scattering components, we can measure how much scattering occurs when you have interfaces in your tissue. So different structures, hair follicles, capillaries, all these will have interfaces that will scatter the tissue. And again, we can come up with a coefficient to characterize for our tissue how much scattering goes on. And the final thing, so we've got absorption, scattering, and then it is traditional to come up with a third factor to characterize tissue. We call it an anisotropy factor. And this is basically when things get scattered, how much of the light gets scattered in the forward direction versus scattered in the backward direction. So we can determine all of these things in the lab. I have a setup. It's two spheres that are butted up against one another. And I put a tissue sample in between. And then I take a laser input and I send that into one of these spheres and it hits my tissue. And some is going to be reflected off the surface and is going to act to heat the inside of this sphere. So we can measure how much of the light is reflecting off the surface. In this sphere, we can measure how much light is heating this sphere, and that will be what is forward scattered through the tissue. Some of it is going to pass straight through, and there's a hole in the outside of this sphere, and we can measure how much light goes through there. So the difference between what gets reflected, scattered diffusely, and goes straight through, and what I know goes in is how much is retained in the tissue sample. So we can measure for a particular wavelength how much of that energy is being absorbed in the sample. And then we're doing some computer simulations. This is just kind of demonstrate what's the way we do it is through a statistical method, Monte Carlo simulations. We send rays into our tissue, so the tissue is to the right of this boundary, and we actually simulate how it would bounce around after we define our tissue properties. And the reason we want to do computational simulations is eventually we would like to get this to the point where we're using lasers in surgical instruments in order to do various things, but we would rather not just try out different combinations of power and wavelength and just see what happens. We'd like to be able to predict it ahead of time, and even though we can do, say, animal trials, before we do things on humans, even then we would like to be able to predict what a good starting point is before we do anything on fuzzy critters. So we in the lab are doing some experiments with equine nasal mucosa. It's horse tissue from their nose. And these are measured values we get for the absorption, scattering, and anisotropy factor. And then we do some modeling where we look at heat conductivity. This is just an equation that tells us for a heat source how that heat gets dissipated in some tissue. So the way we're modeling this to represent the effect is every one of those absorbing constituents in the tissue is taking in energy and it's turning into a heat source. And we can look at how that heat dissipates. And then with our models, we can take measurements with that cool camera. I'll go back one that I showed you up front. So thermal action photons, those particles that the light is made up is converted into heat inside the tissue. And then the temperature at any point in our tissue is dictated by how the heat gets conducted, how much of it is being stored, and then heat dissipation. And one thing, we're doing tests in the lab with tissue to see how real tissue compares, but one thing we miss is that blood that would be coursing through there in a live person that we miss out in the lab. And that could be a significant way that heat is going to be carried away from the site of where the laser hits because it'll heat up the blood flows away. So we're going to have to find a way to account for that. But right now, there's my thermal camera, and here's a slab of tissue, and we're looking at the back side with the laser hitting the other side, and we can actually look at how the back side of the specimen is being heated up due to the laser hitting the opposite side. So if we can compare that with our computer models and get a good simulation, then we can get a pretty good idea that we can predict also the temperature inside the tissue if we can predict it well on the back side. So here is a graph with lots of zones on it for what happens when a laser hits tissue. On this axis, it's the energy that is being deposited into the tissue per unit area. So this is how much energy is going into the tissue. And on this axis, it's how long the exposure happens. So as you might think, for very high energy levels over short time, you get this explosive optical breakdown, whereas all the way over in this corner for long exposure time with low energy, you just get warming. It's nice and toasty and it feels warm. So we can basically look at three zones: photoplasmal effects, where you can cut tissue, you ablate it, take it apart quickly. Photothermal is the area that we're interested, where we're converting the photons into heat. Photochemical is kind of interesting. A lot of people are hopeful that you can actually use light not for heating tissue, but for photodynamic therapy. I don't know if you've heard this, but the idea is that you're using the energy in light not to create heat, but rather to trigger certain cellular mechanisms. I don't know if you've known anybody maybe who has knee problems and they've had a bright light shined on it and they're convinced that it helps. There is no clinical evidence as to why it would help, but a lot of people swear by it. It could be with drugs, there's a known up to 30% placebo effect, so maybe some of that is going on, but maybe there's something more to it. And this is a field of study that people are interested in, just the chemical effects that can be induced by light treatment. But we're interested in here where we're going to heat tissue. And if we look at a graph of tissue changes with temperature, so as temperature increases, 0 to 40 degrees C, we get general heating, And as it gets hotter and hotter, you get all the way through to carbonization starts to turn black, vaporization and burning if it's really hot. And I'll pause here just to say that I've worked on a number of medical devices, and the creepiest thing, I find it very interesting, the most interesting one was when I get to be with a physician doing a cochlear ear implant. So this is, there are some people who lose their hearing because the cochlea loses its sensitivity, which is that structure. It looks like a snail. It's fluid filled, and there are receptors on the inside that detect pressure changes and convert that into a signal that your brain figures out to be sound. Another amazing thing. But what physicians can do now is to take a wire, slip it in there, and the wire has transducers along its length that can be selectively activated. And what that does is it stimulates the cochlea at different parts, so your body thinks it's sensing a pressure change when really it's just picking up an electrical signal, and people can hear again. Now, they don't usually hear like they used to hear, but at least they have some way of determining different pitch. And the way that they do this is actually they cut behind the ear and pull somebody's ear forward. That's always comical to see. And then drill a hole through the base of the skull in order to get into the place the cochlea sits, and then slip the wire in. And then they hollow out the bone and put a receiver under the skin and then stitch it over the top. And that way you don't have any open access bypassing your skin, our first line of defense against germs. So everything is sealed up. But then what a person does is wears a transmitter in the vicinity of the receiver that sends a signal across the skin layer into the ear. And so usually these people will wear a microphone on their hip that'll send a signal up to this transmitter. It's picked up by a receiver. So I got to stand next to a guy when he showed me all of this, because he was looking for some help with a new way of anchoring the receiver to the bone. So that was the coolest thing. The creepiest thing, though, I was next to a physician who was doing throat surgery, and he said to me, "Have you ever smelled the aroma of burning thyroid?" And I said, "Well, I can't say that I have." He said, "Oh, it's wonderful."